All right. Recording, good. Light on. Hello.
Hello yourself. How you doing?
Doing well. How are you?
Okay.
Sweet.
Okie dokie. Are the others here yet?
It's just you so far.
Okay. So I wanted to tell you about a movie that I've seen
Okay.
that may or may not interest you.
Mhm.
It's called The Laws of Thermodynamics.
Oh.
Sounds like, but it's in Spanish, takes place in Spain, in Barcelona.
Okay.
And it's a romantic comedy, and it's about a physicist who's writing his thesis, and he's trying to apply the laws of thermodynamics to relationships, as in an irresistible object meeting and
An unstoppable force.
right, or entropy.
Yeah.
Perhaps you've been in relationships that relate to entropy.
Right.
Right, yeah. So and there's also some particle physics mentioned, and so they actually interview physicists to talk about the different issues: general relativity, third law of thermodynamics, particle physics, quarks, and interspersed with this rom-com in Spanish, though. So,
Okay.
maybe not, but
Interesting. Yeah. I
Yeah.
will definitely look into that.
it's on Netflix.
All right.
Uh,
Very good.
yeah.
So this is the only time I have to eat dinner, so I'm going to put myself on video off till I finish. But I'll
No
listen.
problem.
Sure.
If I have
Sure.
a comment, I'll make sure my mouth isn't full when I talk.
Yeah. Okay. So let me go ahead and start sharing my screen here.
I'm gonna find. All right. This is astronomy. Okay. All right. My note pages.
All right. Here we go. So here's our movie for this week, Looper from 2012. And if you were confused at all by this movie, you're in very good company. After watching this and looking at all of the plot synopses, it is quite a lot to digest. And I may be watching it, 2 or 3 more times before I can fully wrap my head around everything that's going on. But the main premise here takes advantage of what's called the grandfather paradox. And this is a temporal paradox in which somebody is able to travel backwards in time. And the paradox arises is if that person were to meet their grandfather as a child, let's say, and kill him, they would cease to exist. and they wouldn't be able to go back in time in the first place to kill the grandfather. And of course, that is self-contradictory. And this puzzle has been around for hundreds of years.
Wait a minute. The younger self kills the grandfather, or the grandfather kills the younger self?
Well, we'll get into that, but this is just the very rudimentary paradox on which the film is based. This isn't necessarily a plot of the film. This is just where it comes from. This is the original paradox. So let's say you go back in time, let's say 100 years, and you visit your grandfather before he had your father. If you were to kill him, what would happen? You would probably, I don't know, vanish or just vaporize into thin air. It's hard to say because we've never had to experience this. It's just such a bizarre encounter. And so the movie kind of runs away with this, and you have basically several of these paradoxes crammed into one movie. And so it becomes extremely hard to follow at points. And the movie kind of takes a step further to this original grandfather paradox and then says, okay, what if the grandfather now had anticipated your arrival and then killed you before you had the chance to kill him? Let's say when that grandfather now kills you, basically that cuts you off, then you could have never come back to the past in the first place. Does the grandfather now have a memory of that experience? Because it never could have happened. You're eliminating something that happened in the past by doing that, by, let's say, killing your assassin from the future.
Can you, it's interesting. I could understand the movie, but you're confusing me.
Okay.
So can you talk to it, speak in terms of Bruce Willis and, and young Joe?
Okay, yeah. So there's one part in which Bruce Willis is returned to that.
We'll call Bruce Willis Old Joe.
Right.
Okay, old Joe, yeah.
Okay.
So there is a point where old Joe is transported into that cornfield, and he does anticipate somebody coming back in time to kill him. So maybe it'll help if I show the clip here. So I have it saved. Let me dig it up real quick.
Well, if you kill old Joe, then young Joe can still grow old with whatever path he chooses.
Right. Yeah, we're not talking about his timeline. We're talking about, and also old Joe doesn't kill young Joe. He just throws a brick at him and renders him immobile. Here, watch what happens here. It's just a minute clip.
Yeah.
Let me reshare it now.
I don't need to see me. Oh, I set my watch to Arabic numerals in honor of this movie.
Oh, wow.
Actually, Persian.
We can't hear any sound.
Yeah, this is like a quiet part. You'll hear the gunshot probably. And so like this scenario that I'm depicting here. So old Joe is now aware that somebody's coming to kill him from the future. And so he kind of like turns around, lets those gold bars protect him. And so this is what I was kind of hinting at in the slideshow.
What do you mean he, at that moment, he knows somebody is coming from the future to kill him?
So like, so he
Or he's
doesn't-
going back to the past, yeah.
right.
Well, he knew that to begin with, being captured by the bad guys and put in the time machine.
Right. Exactly. So I'm drawing a parallel. The parallel
Yeah.
here, I'm taking a step further with the grandfather paradox and saying, okay, let's say you go back in time to try to kill your grandfather, but surprise, the grandfather knew you were coming and he, let's say, avoids being killed or kills you. And that opens up a whole new like dimension of paradoxes here.
Yeah,
So yeah, what I'm just trying to do is sort of like set a foundation. Like
Yeah.
the movie obviously is much more complex than these two simple examples. But like the primary example is you go back in time and shoot your grandfather. Well, that's self-contradictory because then you cease to exist and wouldn't have been able to do that in the first place. So that's like level one kind of paradox.
yeah,
And another layer to that is you try to kill your grandfather, but he gets you. And the question I brought up was, could you even have a memory of, could the grandfather have a memory of killing his grandson? Because once that shot is fired and now the grandson is dead, the grandfather would be remembering somebody who doesn't exist, which is strange. So that's just, a nested paradox in there.
Well, what happens at, I mean, at the end, when young Joe kills himself, old Joe ceases to exist.
right.
Right.
Well, I have a question. The boy, Sid,
Yeah.
was Sid Baby Joe, or was
No.
Sid
Sid was
Rain
just
Man,
Rainmaker, or whatever.
Rainmaker,
Yeah.
Reign of Terror, Rainmaker? Because there's a young Joe, as the last scene is evolving, sees the little boy after the mother is killed running and hopping a train, remember? And he's crouched down alone in a train car. Well, young Joe was recounting his own life, how he ended up being a looper, and it involved him being abandoned and orphaned and ending up on a train, and then being saved by these other loopers.
Right.
So it made me wonder, was the little boy actually Baby Joe?
Let me,
Except none of the two older Joes did not have his telekinetic powers. So, so probably not.
Yeah, so this woman who is from the farm has a son there,
Yeah,
but you know, young Joe's already existing in that time. And so yeah, the problems arise when you're doing the time travel, when you're doing the time travel, when you're like hopping into that box and then being transported, like just that act, you know, causes a lot of confusion.
But you're saying, so in 2044, Sid was 10 years old and young Joe was 30 something already. So they're both existing in 2044.
Right.
Yeah, but so is old Joe, you know, even though he's come back from the future.
Yeah, technically you can have a whole continuum of Joes at each different age.
Right, but there's no evidence that young Joe or Sid time traveled. At least they didn't present that in the movie.
No, they didn't present it, but it may, because of this railroad car scene and how young Joe described his childhood, it made me wonder, you know, or was he just as he's standing there deciding, you know, who to kill, and is he just imagining what the little boy's life would be like if the mother was killed?
Yeah, I hadn't put that together with the train in both their lives.
Well, I did, and then I went back to where young Joe, middle Joe, is telling the kid about his life, because the kid asks him, "Where's your mother?" And you know,
Yeah, and it's another really crazy thing that I'm not even sure if I'm going to have time to dive into, because it's just, this is where it gets like really sci-fi. It's like when the young child is in the farmhouse and he's able to like levitate objects.
yeah.
And that's sort of a little out of the scope of
yeah, that's very sci-fi. Time travel is not sci-fi, right? That's not.
Yeah, time travel is pretty plausible in some respects, but yeah, the levitating thing that kind of lost me a little bit.
In what respect is time travel plausible?
So time travel can be plausible at the quantum level, and so you have superposition, for instance. If we can say that, let's say, two electrons can be in the same in a different place at the same time. So you can have like electron in this room and an electron out in Andromeda galaxy, like the same electron existing in two places at once.
I mean, by the probability, you were talking about the probability principle?
That's right. The probability, it's a wave function.
Heisenberg?
Right, uncertainty principle. We can't pin down the electron, and it is possible that the electron can be two places at once. And if that's the case, that means one is going out into some other timeline or some other point in time. Because Andromeda, let's say from now, is 2.5 million light years away. So if we were to, let's say, observe that electron, we'd be looking at it 2.5 million years ago. And so it's existing in the past and the present at the same time, according to somebody on Earth.
Yeah. So one descriptive phase for that is time travel.
Yeah, you can say the electron is time traveling. Like it exists in the past and it exists in the present. And that's just time traveling into the past. We can certainly time travel into the future. That's been experimentally verified That's just time dilation, in which you can experience time more slowly than somebody at rest by moving at relativistic speeds. The clocks on GPS satellites tick more slowly than the ones down on Earth.
Right.
So we can certainly travel into the future.
Do the clocks have to, is there a calculation and a compensation for the difference with the GPS satellites?
Yeah, there is a discrepancy. I'm not quite sure what the numbers are.
They're pretty small, but the fact that it does exist is a proof of Einstein's general equations of relativity.
Exactly. Yes.
And in the movie Interstellar, maximized this thing with, traveling, near the black holes and coming back. The protagonist came back and his younger daughter was older than him.
Yeah, exactly.
Right.
So I wanted to just share, and this is sort of the connection between what happens in the movie, or just what happens generally with a grandfather paradox, to quantum mechanics, and how you can sort of resolve the initial problem I posed in the slideshow. So this is a video by Minute Physics. It kind of wraps it up nicely.
As far as we know, time only moves in one direction, forward. But if you could loop back to visit the universe at an earlier point in time, a famous paradox arises. What if you killed your grandfather when he was a child? Then your father or mother wouldn't have been born, so you wouldn't have been born, so you wouldn't have been able to go back in time to kill your grandfather in the first place. Paradox. The simplest resolution to the grandfather paradox is that when you go back in time, you're actually not going back into your own history, but to a copy, and everything you do there influences the new alternate future of that universe, not your own past. But that's boring because it just avoids the paradox. If what you do when you go back in time actually influences your own past, and the effects of your time travel do loop back to the present, future, past, no problem. Let's just follow the paradoxical timeline through beyond its paradoxical conclusion. You go back in time, kill your grandfather, thus you aren't born, so you can't go back in time, thus your grandfather isn't killed, thus you are born, so you go back in time and kill your grandfather, and so on. I'm showing this as a looping linear series of events, but really it's two entangled histories happening in parallel. Is that even possible? Well, I don't know about the time travel part, but subatomic particles regularly do multiple different things in parallel. It's called quantum superposition and is responsible for the weirdness of the double slit experiment, many properties of atoms and molecules, fusion in the sun's core, and so on. So if the universe were to exist in a superposition of two states, your grandfather's alive and your grandfather is dead, then the natural result is a superposition of two states. You're born and able to go back in time to kill your grandfather, and you're not born. And the natural result of these is a superposition of two states. Your grandfather is dead and your grandfather is alive. And so, at least from a logical perspective, this looping timeline is entirely consistent and there's no paradox. And a similar paradox-free solution can be obtained by viewing the problem as a steady state solution to a Markov chain. But I won't go into that here. Now, of course, nothing about these solutions to the grandfather paradox suggests that closed time loops are actually possible. In fact, some of the implications this kind of time loop have in the study of complexity theory seem to suggest that time loops, and thus time travel into the past, must be impossible. But the main point is sometimes we think a situation creates a paradox when it doesn't. And really the only paradox is how our thinking can be twisted enough to dream up time traveling murderous grandsons, but not twisted enough to think about twisting time.
Well, that's a lot of food for a lot of time thought.
It is. The main point not this whole Mobius strip thing, but the main point is that yes, subatomic particles can
it's called quantum superposition.
Take advantage of this time traveling aspect. Because space and time are both interlinked. So if you're in two different points in space at the same time, you're also in two different times.
So, I mean, isn't this the same kind of jump that's done with, well, wormholes are possible because, you know, you can get something like that maybe at a quantum level, but to move from the quantum level to the, you know, to the Einsteinian level of, you know, that's a big jump, that analogy, right?
Yeah, definitely. And going through wormholes is just as plausible, but not, or sorry, going through wormholes is very unlikely, but it's not prohibited. Having a copy of me exist somewhere else in the universe is also not prohibited, but it's extremely unlikely. It's extremely unlikely that I quantum tunnel through the door, for instance. Because, you know, my body is made up of electrons and other subatomic particles, and there's nothing that can stop all of the particles making up my body just exists somewhere else whenever they want. Because you can't pinpoint every single atom that makes up my body with extreme precision. There is a non-zero probability that I can walk through a wall. And, you know, that sounds absurd, but if you really break it down into the behavior of quantum mechanics, it's not against the rules of the universe.
You know, Boltzmann brain?
Yes.
No. What is this, Stuart?
You know, it's the same thing that Ryan's saying. The Boltzmann brain argument suggests it's more likely for a single brain to spontaneously and briefly form in a void than it is for the universe to have come about in the way modern science thinks it actually did.
Yeah. It's pretty unfathomable, but it's a sound argument.
Another sentence that says the same thing is in a physics thought experiment, a Boltzmann brain is a fully formed brain complete with memories of a full human life in our universe that arises due to extremely rare random fluctuations out of a state of thermodynamic equilibrium, which is what you're basically saying, right?
Mm-hmm. Yeah. And so quantum tunneling is something we probably never experience on our day-to-day lives, but it's literally the process that keeps the sun shining. Without quantum tunneling, we wouldn't have these proton-proton chains releasing energy every second, heating the earth, lighting, you know, giving daylight. The reason we can see in the daytime is quantum tunneling. That's a huge, that has to happen in the core of the sun in order for it to shine.
So how does it work in the sun?
So I think we, let me see. I'm trying to find the best article that explains this.
Oh, here. Oh. So this is on.
Oops. Good old air blocker. Oh, turn it off. 1 second. Okay. Wow, so many pop-ups. Okay. So I think we visited this diagram maybe last week or 2 weeks ago, where we have two hydrogen atoms coming together, forming some helium, and releasing energy as light, visible light. But in order to do that, in order to push two protons together to form helium, there is a lot of, I think it's a potential wall that needs to be overcome, because this has to go, I can really dive into this. This goes back to like fundamental forces. Two protons are both positively charged. So when they get really close to each other, they're going to want to repel. And there's a really strong force urging them apart. They don't want to be together. But sometimes what quantum mechanics can do is allow them to touch and fuse. And this allowance is because they jump over a certain potential, like a barrier. And classically, they shouldn't be able to do that. They shouldn't be able to come together because they're going to be repulsed. But quantum mechanics is like a little loophole. It says, oh, no, just kidding. Like there is enough energy. You can fuse. I think perhaps a video might illustrate this a little bit better.
Do you know that if the sun were fueled by combustion of, say, gasoline or wood?
How the
Did you know
sun
that if
works.
the sun were fueled by combustion of, say, gasoline or wood, it would burn out in just a few millennia? So how is it still here after 4.5 billion years? Physics. The sun is like a big nuclear submarine in the sky. That's right, it's fueled by nuclear reactions that fuse hydrogen atoms together into helium and other heavier elements, releasing huge amounts of energy in the process. In this way, the sun is slowly converting its mass into energy in the form of sunlight, and it has more than enough fuel to last billions of years. But nuclear fusion is no walk in the park. On Earth, we need to heat hydrogen up 100 times hotter than the sun to get a fusion reaction. So how does the sun do it? Quantum tunneling. There's a small chance, which I'll explain later, that hydrogen atoms, even if they aren't quite hot enough for fusion, will fuse together anyway. And the sun is so big and has so much hydrogen that these small chances happen all the time. And that's what keeps the sun energized. So when the sun shines tomorrow, give thanks to quantum mechanics.
So basically, there is so much hydrogen atoms. There are so many hydrogen atoms in the sun that even with a minuscule probability of two protons fusing together when they really shouldn't is large enough that it happens regularly. It's like, how do I do this? It's like playing the lottery, which is an extremely rare occurrence, but you make it a regular occurrence by buying millions upon millions of lottery tickets. And you're like, okay, you're bound to win if you buy that many.
Yeah,
So,
that's kind of like the old line, anything that's a possibility, given enough time, is a certainty.
yeah, there you go. And so in this case, it's an amount of quantity. It's like given enough hydrogen atoms, right, this rare occurrence of quantum tunneling can happen normally. And so this is like the best like cartoon, I think, for quantum tunneling. It's like, you must be this hot to enter fusion. You must be this hot to achieve fusion. And then quantum mechanics is like, well, based on the uncertainty principle, you can't really tell where we are. And so they fuse anyway. And so it's like actually tunneling. So they like dig a tunnel and go underneath the gate. I thought this was kind of humorous, but this is a really good interpretation of like what happens.
Good.
So the other slide I wanted to present, which really intrigued me, was how do we keep track of time? And I thought of this because in the movie, right, when he's in the cornfield, he's holding a pocket watch, an analog pocket watch. And I thought to myself, I was like, how accurate, are these devices? And why is it that in 2044, these are the instruments that are being used to keep time? And how can we be sure they're even accurate? So the way a pocket watch works, or many other wristwatches, is you have a little piece of quartz sometimes, and it vibrates at a pretty regular frequency. And you can say, all right, 1 second is going to be exactly this many oscillations of that crystal. And we've been using that for probably centuries, I believe. And then, a few decades ago, the advent of atomic clocks became the norm. And what atomic clocks do is they have a little cesium atom. And the cesium atom has an electron in its outer shell. If you picture, let me pull up an image of this. If you picture a cesium atom with like the concentric rings, it kind of looks like, hold on, like this. So here's the cesium atom, and you see that all these shells are filled with electrons, these gray dots, except for that very outer one, and there's just a single electron in that ring. And it's not stationary. It like wobbles a little bit. So that outermost electron is jiggling constantly, but it jiggles so regularly. It's got a very precise frequency. And not too long ago, we decided we're gonna define 1 second to be exactly 9,192,631,770 of those little oscillations. And that's the SI unit of a second. That's what we have now. So, yeah. So
SI, what does SI stand for?
Scientific International, like International System of Units. Like we have the kilogram, the meter, the second, Kelvin, candela, mole, ampere. So yeah, a 1 second, if anybody asks you how long is a second is exactly, by definition, in this little box here, 9,192,631,770 oscillations of the little electron in that cesium atom.
What does that mean by 10 to the minus 13, the Allen deviation?
Yeah, so that's the deviation from, I guess you'd say, typical clocks.
Is that the optical clock, the fourth one? No.
Yeah, optical. And so the smaller the deviation, the more accurate it is. So 10 to the minus 13 is ridiculous. It's, here, they give you a context here. 10 to the minus 15 seconds is what 1 second is to 32 million years. So if 1 second was a femtosecond, a real second would pass in about 32 million years.
Pretty accurate.
Yeah, and I learned another thing. In 2019, I think they've come up with the most accurate clock to date, called a quantum clock. And this has an uncertainty of 9 times 10 to the minus 19. And that is about 1 second to 320 billion years. So it'll lose or gain a second in about 320 billion years. And so it surprised me. It's like, why isn't it in Looper that he's not carrying around like a really sophisticated device that says precisely what time it is? He's just using an old-fashioned pocket watch.
Well, this is a guy who was learning French. The character himself I mean, maybe there's a particular history because that is a particular numerical face.
I see.
But this is a guy who has other interests, let's say, above and beyond just, being a killer automaton.
Just as an aside, I'll throw it in just
Yeah.
while we're on the subject. In the original script of the movie, he actually did go to France first, and they had that there before China. But I was reading about it, and what happened was they were running out of money when they were making the movie.
Oh, yeah.
The Chinese company backed the movie, and they had to have it all in China, that whole section.
Right.
Oh,
Yeah.
interesting.
That was in the notes, in the Amazon notes, right?
Mhm.
I know, I just read it somewhere on the internet, but
Yeah.
they have Amazon has notes.
Yeah. So do you watch Amazon movies
Yeah, sometimes.
on your computer?
Yeah.
Okay. So in the upper left, it'll say something about trivia and cast and X-ray. Or if you just
I actually just watch them on the TV, so I miss all that. But if you watch it on
Okay.
your computer, you get that. I see.
yeah,
Mhm.
upper left,
Got it.
or just press on the upper left screen, and it'll those who's the actors in the particular scene and what the pertinent trivia is, and if you press on that, then you'll get a whole thing of trivia about the movie, stories about the movie. Yeah.
Yeah. The other thing I wanted to point out in the movie, which is a really crazy thought experiment, is how memories are formed. How do your memories evolve and change over the course of traveling through time, backwards or forwards? And so I'll start with this clip here, where they're in the diner and old Joe meets young Joe and is trying to like talk some sense into him. Yeah. So I'll watch this part here.
And Beatrix.
Yeah, Beatrix. And he says, oh, Jen would have been fewer letters.
Yes.
Okay, here we go.
You know what's gonna happen. Not on this already. So we start talking about it. You're all day talking about a big diagrams and straws. Doesn't matter when something changes your body, so it do not change your memory. Now here's a more on this. Then they get to the present moment and they're instantly clear again. Remember what you do, what you do. This is a precise description of a fuzzy mechanism. It's missing. Oh, I know. Bounce happens later.
And this was really puzzling for me to think about, because little Joe, like his young Joe's life is influenced by his encounter with himself.
This is why this is not permitted on Star Trek with the Prime Directive.
Yeah. And he goes about saying, you know, his memories, it's like young Joe is like, I could alter your memories. If I just like wave my hands around and do something absurd, like that's gonna form memories instantaneously into your head. And I was like, wow, that is like so bizarre to even think about, how you can manipulate your future self's memories instantly by just doing whatever. And it's really surprising, like old Joe says, you're going to do the following. And how can he know? Because this encounter now is novel. This has never happened before.
It changes the timeline.
Yeah. I think a good example of this is the story of Oedipus by Socrates, where Oedipus meets the soothsayer and he goes, you're going to kill your father and sleep with your mother. And how can the soothsayer possibly know that unless he was able to predict Oedipus's reaction to the news?
Mm-hmm. Exactly.
And yeah, I think that's crazy. Like, I'm trying to think of others, like a scenario in which I could form new memories by, you know, doing something in the present. And then he finishes the end of that scene. I didn't film, but at the end of that scene, he's like, yesterday is 30 years from now. Like 30 years from now, you're going to be kidnapped and put back into this diner. And I think that's, you know, where the title Looper comes from. Like, you can just cycle endlessly.
Didn't, you know, I was just looking at somehow what you said reminded me of Feynman, Richard Feynman.
Feynman, yeah.
Yeah, and his diagrams, Feynman, of the sum of overall possibilities, the path, integral formulation of quantum theory.
Yeah, the path integral. You have to sum over all possibilities.
Right.
And that's a great point, where you get like the position of an electron is you have to account for everywhere in the universe that it could possibly be. And then, yes, it's certain that the electron exists in the universe, but that's pretty much the only certainty you can get.
Well, that, I guess if you have 10 to the 100 universes, that's pretty certain to say that the electron exists in our universe. Is it limited to our universe?
So that's a good point. You would have to specify what is your enclosed system.
Mm-hmm.
What is your isolated system? Because if I just say this whole room is the universe, and I have, I don't know, a grain of sand, and I don't know, I don't know what couch cushion it's under, but I have to say for certain it exists in the room. It may not be under cushion 1 or cushion 2 or both at the same time or neither, but it's definitely in this room because that's all there is. That's 100% of the volume I'm considering. I assume this is the isolated closed system. Yeah, it gets quite weird when you examine infinitesimal probabilities For instance, this is a really cool example that one of my thermodynamics professors had told us as a class. He said, there is a chance that all of the air molecules in this lecture hall spontaneously migrate to one corner of the room, leaving the rest in vacuum. And we're like, what? How could that possibly happen? And he's like, it's the law of thermodynamics. We are in a probability cloud. You know, the gas that is in this room is on a distribution. It's not certain that they have to be in this arrangement.
Yeah.
Probability is very low of that happening, but it's
Right.
but it's
Or without an external force.
Yeah. Without an external force, there's probably like 1 in 10 to the 50 chance that it happens, but it's not zero. It's not zero.
Yeah.
And that kind of blew our minds. And, you know, that's why I remember it to this day. It was just such a crazy fact about statistical mechanics.
You know, there's one other statistic that, you know, when you were going back to that time thing, when you were saying, you know, it's like 1 second to, you know, 1 billion years or something, you know.
Right.
That really made the point. If
Yeah.
you say that the Earth and the sun are 1 inch apart in that model,
Mhm.
how far is it to the nearest star?
1 inch. So I can do a quick calculation for you. 4 times 6. All right.
Well,
So
before you do the calculation, what's just the gut feeling that comes to your mind as an answer?
I feel like it would be,
Without the calculation, just what's the gut?
yeah, several hundred miles.
It turns out it's 86,000 miles.
Wow.
When
I
I
didn't-
heard that, that tells me, yeah, it's far away, a star.
Wow. I never put that into that kind of scale before. That is really bizarre. That's mind blowing.
Yeah, I never checked, double confirm that, but I heard it from a reasonably reputable source. But you can calculate it in just a few minutes, I guess.
Yeah. So the nearest star is something on like 10
4
to
light
the,
years.
right, 10 to the 13, let's say, miles away.
Mhm.
And then Earth to the sun is only 10 to the 7. So it's a ratio of 1 million. So 1 million inches. Wait, no, that doesn't make any sense. Wait, maybe.
Now you're going to calculate it and find me
I-
totally wrong.
No. It's the right order of magnitude. I think it's maybe like 15,000 miles. But it's the right order of magnitude, tens of thousands of miles, which is ridiculous. That is a really great fact. I want to share that with my friends. So before we wrap up, just in the last 5 minutes, sort of concluding thought for the slideshow here, I'll share one more time, is, you know, maybe one day we do encounter people from the future, but we can't do that until the very first time machine is built. Because if we experience a time traveler, let's say today, let's say somebody from the future comes and meets us today, then when was that time travel, when was that machine built, basically?
currently or in the future?
Yeah, it would have to be at least, hold on, let me think about this again. I want to make sure I'm saying what's accurate here. Because you would need a way to get back to where you started. That's the assumption. The assumption is you have to get back to where you started.
Why
so
is that? Why is that an assumption?
Yeah.
I think, I'm not sure where it comes from. If you were to just go back into the past and stay there, I feel like there's something wrong with that.
Yeah, I think there's something wrong with time travel anyway. But you're right. And when you do it with general relativity and different reference frames, you have time travel in essence.
Right. Yeah. You can always time travel into the future. You can time travel right now, just at the speed of the normal universe. So, I mean, we're all three of us are traveling through time the same way everybody else is. We're just going into the future 1 second at a time.
Mm-hmm.
Going into the past is where you have a lot of red flags come up. So yeah, lots of movies where somebody travels into the past are often problematic for a number of reasons.
Mm.
Do you remember a book that came out about 25 years ago? You probably don't remember it because you weren't doing this stuff. It was called The Physics of the Impossible. Again,
Yeah, by Michio Kaku.
Yeah. Didn't he say that a few things are not possible by the laws of physics? I know precognition was one of them, but I thought time travel one way.
Yeah, reverse time travel, I would think, is impossible. I haven't done much reading on that. The things I have done reading on, which I know are certainly impossible, are two things. You can't move information faster than light can in a vacuum. And you can't violate the second law of thermodynamics. You can't decrease entropy. You can't flow from a hot state into a cold state, into a high energy state, into a low energy state. You can't go from disorder to order spontaneously without doing work. So those two things I believe are definitely
What was the
impossible.
first thing again?
Breaking the speed of light. That is, send information faster than C through space.
And why is it impossible?
So you have a lot of things that go wrong. The first you can think of is like time dilation. And this is probably tied into going back into time, is as you get closer and closer to the speed of light, time for you slows down. It goes more and more slowly. Eventually, you're at the speed of light and time stops. Time stops and light experiences no time at all. Now, let's imagine, what if you were to exceed the speed of light? What would happen to your clock? Like intuitively, it would maybe go in reverse. If it did that, you'd be instantly returned to a time in which you weren't traveling faster than light. And it's just a logical inconsistency. If you continue like the mathematical, how do you say it, curve for how time acts for you. The other thing is, like, you need to be massless in order to travel at the speed of light. And you can't go less than 0. If you have negative mass, then something's wrong. Then our whole notion of physics is broken. It's impossible not because like something is preventing you, but it's impossible because the way we operate forbids it. Like, if it were possible, then nothing we know is true. Then we have to scrap all we ever knew and learned about the universe.
Yeah, that comment about, are the laws of physics the same at every place in the universe is an interesting question.
Yeah.
I'm gonna run. See you next week. What's the movie
Okay.
we're gonna do next week?
Haven't looked at it yet. I will let you know tomorrow. Tomorrow
Okay,
will
sounds
be
great.
posted.
Take care. See you next week.
All right.
Bye,
Stuart.
Stuart. Hello to Owen. So, oh, yeah.
Yeah, if you ever get the time, if you want to like take a screenshot of this or something, but
Yeah.
this is a,
Ooh, didn't show
Sort
up.
of.
It didn't come up.
let me undo it then. Okay, there we go. So this is sort of a synopsis of what happens in the movie. Young Joe kills Bruce Willis and kind of goes through a loop.
Okay. Just wait a second. My doggy wants to go out.
Okay.
I'll be right back. Sue, what is it? And my dog gets everything she wants. So, okay, so wait a minute. So young Joe kills. So when is that? Oh. But he doesn't kill Bruce Willis. Sid becomes the Rainmaker. His life in China. Meets wife. Rainmaker, killing loopers. Yeah. Wife killed, sent back without bag. Fails to kill, learns about Rainmaker. Right. Young Joe lives unknown life. Sid becomes Rainmaker, wants to kill loopers. Oh, so the kid becomes the Rainmaker, wants to kill loopers because they've killed his mother and all that, one would think.
Yeah. I looked at a lot of other summaries and people argue whether it's logically consistent or not. And some people say it breaks down at points.
Yeah.
So I don't know. It's up to your interpretation.
Right. Well, it's, it's a movie, so it's a lot of poetic license.
Yeah, definitely.
Yeah. Yeah. Huh. Well, Stuart can discuss advanced physics with you more than I can. So it's good that he's here to add that dimension, to use a word. Yeah. Yeah.
All right. Well, that's
Hmm.
all I have for my slides today.
Well, thank you. Excellent. Added a lot to the possibilities, to the interpretation of the movie. Yeah. Yeah. Okay, well, wait to see what's coming up.
That's right. Yep. I'll let you know tomorrow.
Sure.
And they'll be posted on the website.
Yep. Okay. All right. Thanks very much. So
Sure thing.
is that music on a behind you?
Oh, it's the sync running.
No. I physically see a white the top of a white
Oh,
sheet.
yes,
paper.
it is. It's a piano behind me.
Oh, yeah,
Yeah,
yeah. So you play?
I do. Yeah.
Oh, good for you.
Thank you.
Yeah, yeah. All right. I did it in school. Stuart used to play. Oh, Ann plays the flute.
Okay.
Yeah. Yeah. But and so you're in graduate school now?
I finished grad school last year.
Uh-huh.
I'm working to become a teacher pretty soon, probably this fall. And I think I'm going to be moving to Florida. I'm in Arizona right now. I'll probably be in Florida by the end of this year, but I'm still going to do Sci Fi Explained every week. Just like
So teaching at what level?
Hasn't been decided yet. It's going to be middle school or high school in space and earth science.
Well, good luck with that.
Thank you.
Yeah, we clearly need more science and in particular physics.
That's true.
Yeah.
Yes.
Yeah. My dear late friend Leon Letterman used to say, physics first.
Oh yeah. Totally.
Yeah. Because the rest of us, took biology and then chemistry and then physics.
Mm-hmm.
But physics is the basis of everything.
That's true. Yeah.
Yeah. Yeah. Yeah. Florida. You don't want to be there now. Yeah. All right. Well, okay. Speak soon.
All right. Yes. I will see you next week.
Yes. Okay. Thanks.
All
Bye.
Bye.
Thanks very much for what you do.
You're welcome. My pleasure.
Thanks. Bye.
Bye.